I'll wait till it starts.
We are recording.
We're correct. Okay, we are recording. Okay. So hi, everyone. I guess we have 20 participants minus. So if I take myself up, that's 19. That's interesting. COVID-19. So we have 19 participants plus myself here. So that's pretty good. So the attempt here is to keep this as non-technical as possible. Okay, so that's one thing. I'm looking for your feedback on that. If I could make it less technical, but still get the points across that you found interesting, then let me know. So, but here we go. After the talk, not during the talk. All right. So here we go. It turns out that you know, we sometimes think that, you know, our age is the age we live in, or the time we live in, is unique to the world, but it turns not. As far as humanity is concerned, this pandemic's not our first rodeo, right? If you just take a look at the last 2,000 years, the Antonine plague, or sometimes it's called the Galen plague, in the Mediterranean region, Asia Minor, Greece, Italy, and Egypt, was really the first, well, it was the first smallpox pandemic in the last 2,000 years. And it had a global death toll of about 5 million people. Okay, so I'm going to call that a GDT. So that was actually the start of the downfall of the Roman Empire, if you have read any of the history. There was a plague of Justinian in the Byzantine Empire, and that lasted a couple of years, and that was the bubonic plague, and that killed about half the population in Europe. There was another bubonic plague, the Black Death it was called, and that was in the entire known world got that thing, and that was about 200 million. Death toll estimates range from 100 million to 200 million. There was 7 cholera pandemics in the last 2,000 years. The most deadly of that occurred just before our Civil War. So the global death count the death toll was 1 million. In the United States, we probably had about 150,000. There was the flu pandemic, which occurred at just before the turn of the last century. And that was really the first epidemic in the age of bacteriology, where we sort of knew what was going on. And the GDT there was about 1 million. The 6th cholera pandemic came in the early 1900s. Interestingly, it killed 800,000 worldwide, but only 11 in the United States, because we had figured out what caused cholera. Well, everybody had figured out what caused cholera because of a scientist, John Snow, in London. But we in the United States, we had clean water everywhere, pretty much. So only 11 people died in that one. Then we had 3 flu pandemics that killed a lot of people around World War I, 56 to 58, and 68. The one thing about, we don't know for sure where this one started, probably actually in the United States, certainly not Spain, we know that much. This 56 to 58 started in China, and 68 in Hong Kong. About 50 million people worldwide died in the 1918-1919 pandemic, and that was about 1 million at least people in the United States. 2 million people died worldwide in 56, 58, and that was about 70,000 people in the United States. And in 68, about 1 million worldwide, and probably another 60 to 70,000 died in that one. And then HIV/AIDS killed 36 million. This is the peak, worldwide peak, 2005 to 2012. That's a little different than the peak just strictly in the United States.
1,000 in the United States, that's more than World War II. No,
Yeah, we
it's
lost
Civil War. I mean, the First World War. No, where am I?
we lost 700,000 people to AIDS so far in the United States.
Yeah. You had a fair idea.
So let's talk a little bit about what a virus is, first of all. A virus is a parasite. It can't live outside of a living organism, at least for very long, just a few hours at the most. What a virus does is it hijacks, takes over some of the machinery of a living cell to reproduce itself. That's what it does. And so this is the most technical part of the talk coming up here. In order to understand what a virus does to us, I have to show the machinery of a living cell, what I just called here, machinery of a living cell. So what is it? Well, so the three things that we're going to have to discuss and know about is DNA, RNA, and protein. These are all polymers. Polymers are things that are units that are all strung together. So if you think of a single pearl, and then you put one after the other on a string, so the string of pearls will be a polymer of a single pearl, okay? So DNA is a polymer of nucleic acids, and so is RNA, but DNA is a double helix, RNA is a single helix. And so if you consider DNA a library, each gene, if you will, in our library, we all have the same DNA. Each gene in our library, the human DNA, is a book. And if you want to convert that book, that's the information to make a protein. So if you want to do that, you make a copy of the book, okay? And then you take that copy and you make the protein. Protein is made of amino acids. So nucleic acids, amino acids. And that translation process is what most of the viruses we're going to talk about today interfere with. So let's go on. So let's draw this machinery to scale. So for human DNA, which is 3 billion units, if you will, 3 billion nucleic acids.
Yeah, he's on Zoom.
Oh.
He's gonna.
It would probably be better if everybody muted themselves. So DNA is 3 billion units. RNA, if we draw it to scale, the biggest RNA is about 70,000 in humans. So the biggest book, if you will, make a copy of that book or that gene. It's about 70,000 nucleotides long, and that makes a protein that's about 27,000 amino acids long. So really, this should be smaller, the protein, but I can't make them any smaller and have them show up. So, but it gives you some idea of what we're talking about here. Now, there are many important differences between DNA and RNA in addition to size. I'm not going to talk about them, but I do want to talk about one of the most important differences, and that's stability. DNA is very stable. It degrades very slowly in a living cell. In a sense, DNA in a living cell will last as long as the cell is alive. RNA, however, is very unstable, very fragile, and it degrades very quickly. So when you make a copy of a book into RNA, it has to be translated into protein within an hour, or maybe 2 at the most. And then it gets degraded. And that's, there's a lot of good reasons for that, but we're not going to go into that, but that's just the way it is. So very stable, very big, RNA, small, unstable, protein, that's what we need to live. Okay. All right, so I'm going to go on here. So what are the properties of a, just a moment here. I don't know where this little red thing came from, but anyway. So anyway, how do viruses work? This is the third thing. A virus is either a small piece of DNA or RNA, okay? This DNA or RNA, we're gonna, so we have to use some of this, we have to call it something, and we call it a genome. So it's not a very big word, so you can just remember that. So the DNA or RNA of the virus is called a genome. Our genome is our whole 3 billion bases of DNA, okay? But a virus is just a small piece of DNA or RNA. Viruses are very efficient. They travel, quote unquote, very light. They only take what they need to do in order to get into the cell, take over its molecular machinery, multiply, and then get out. And make an escape means after the cell is dead. So, and it makes its escape then. Now, there are almost no universal rules, but here are 3 of them. Travel kit always includes the genome. It's always surrounded, the genome itself is always surrounded by a protein shell, and we call that a capsid, okay? And so that's something else that you can remember, or you can just say, okay, it's got a protein shell, whatever you want to call it. Now, some viruses also have an overcoat of fats, and that has a name called a lipid bilayer. And it's made from stolen pieces of the membrane of the cell that the virus just killed. Okay, because every membrane in your body is surrounded by a lipid bilayer, and that's what the protein, that's what your membrane is. So let's look at one specific virus. Let's look at the RNA virus that's named SARS-CoV-2. That's the name of the virus. That virus causes COVID-19. So you've got the name of the disease, which is COVID-19. The name of the virus is SARS-CoV-2. So here's an artist's drawing of the virus that causes COVID-19. Now you've seen this on TV a lot, I know. So it is a sphere, okay, more or less, but you'd barely see it cut open, sliced open in the middle, so you can see what's inside. So this is what we've done here, though. Very nice picture. So that's the RNA genome, and that's 30,000 units long. 30,000 units long. 30,000, each one of those little dots there is a nucleotide. So here's the protein capsid right there. And I'm going to show you. So that's it right there, that little blue thing. These things don't really have color. All right, but that's what they are. That's the protein coat that's around it. And then when it leaves a cell, it grabs onto the membrane of the cell it killed, and that coats it there. Now, sticking through the protein is this guy. So there's the lipid bilayer, and then this guy is this famous spike protein that you've probably heard about. And it matches a receptor. Don't need to worry about the name of the receptor. It has an acronym, ACE2, if you wonder about that. But in any event, so there's a picture of it. Now, so how, let's take a look. Now I'm going to look at the genome itself. So we're going to look at this guy, okay? And say, oh man, what are we going to do here? Well, so I'll show you. It's a long, right? For an RNA virus, it's long, and it codes for several proteins. That is to say, it has information for several proteins in it. And you'll note when I'm about ready to show you here, this picture, note the spike protein. And the spike protein is what is necessary for this guy, this viral particle to replicate. If it doesn't have the spike protein, it can't hurt you because it can't get into a cell, and that's it. It's done. It's over. Okay? So, but if it's got the spike protein, then it can get into a cell. And so here is the genome, 33 units long, and we've got pieces of this, each to make different kinds of enzymes. And this one right here is the spike protein. So everything else in here is an enzyme. There's one protein called the spike protein. And this piece right here, I'm going to go back up here, right at the very top, it matches perfectly with the receptor in the lung cell. Okay, it just really wants to bind tightly. Okay, so now we're going to discuss. So that's the thing that everybody targets, except for one of the manufacturers right now trying to make a vaccine. They target this guy because if you destroy the spike protein, it's done. SARS-CoV-2 can't hurt you. So how does it kill people? Well, the virus generally reaches the host through the air and enters the upper respiratory tract here in your lungs through the nose or mouth, unless you wear a mask. Now, sometimes the particle it's in droplets of water, right? You sneeze or whatever. Sometimes the particles are so small they can still get through the mask, but the number of viral particles in that really small droplet of water is usually not enough to actually cause you to have disease. Okay, so that's why a mask is so important. Now, if you want to not have anything, you wear, instead of a cloth mask, you wear an N95, which covers every kind of particle where the virus could get in. Now, the spike protein produced from, so now it gets in here. right, gets in your lungs. The spike protein that comes through the lipid or fat envelope matches the receptor nearly perfectly. It binds to this receptor, this protein, just like insulin binds to a receptor on your liver cell, okay? And controls glucose. We all have, all of our membranes have proteins that stick out that, and a lot of them are receptor proteins, and the lung cell has a receptor protein for a particular thing that actually increases blood pressure. That's what ACE2 does. But in any event, now what happens after this viral particle then binds to the receptor, that lipid, the fat overcoat, the fatty overcoat of the virus and the fatty overcoat of the lung cell, that allows them to merge. And now the viral particle gets into the host cell. And the viral RNA then is translated into proteins, all those proteins that we saw, okay? Including the enzyme, an enzyme called the replicase. I'll just go back to it. That's right here. The replicase, what it does is it actually makes thousands of copies of the viral RNA. So now you've got thousands of copies of the viral RNA, and they use the machinery of the cell, the lung cell, to make more copies of the enzyme, more copies of the spike proteins, and more viral particles, so it makes the capsid too. So you've got thousands of these viral particles inside the lung cell. Finally, the lung cell will die. And as soon as it dies and basically explodes, the viral particle will shoot through and grab some of the membrane of the now dead lung cell, and it'll be encapsulated in a fatty layer. Now, it's even worse than that, though. You think that that's bad enough, but it's not, because once a few lung cells die, that triggers an inflammatory response. It's not antibodies, it's an inflammatory response. And so the macrophages and killer T cells that descend on the lung, the area of the lung that are dying, it kills good lung cells, okay? Cells that aren't even affected by the virus itself. And so what happens is that the two combined together creates a severe case of pneumonia, essentially, and causes death of the human host. And so that's why now, we didn't know this at first, but we actually do something that you wouldn't think would be something you would want to do. You would give a person who just started getting severely sick with COVID-19, you'd give this person steroids to decrease the immune response, which is something you say, I wanted to make antibodies, but no, you'll kill him. He'll die otherwise. So you give him steroids. And you may not have known that, but when President Trump went into the hospital, that was one of the things that they gave him right away. Okay, so there are a lot of other viruses, of course, and we're just going to look at a few. There are DNA viruses and RNA viruses. DNA viruses cause smallpox, herpes, the common cold, and chickenpox. RNA viruses cause polio, measles, again, a common cold. So the common cold, you can get a cold and it could be a DNA virus or an RNA virus. Not that it matters to you so much, but you could actually determine if you wanted to get the test. You can get the flu, rabies, hepatitis C, AIDS, Ebola, the first SARS, and then COVID-19. All those are RNA viruses and many more. Now, how do we fight viruses? Well, for most of human history, we've been around a long time. Our immune system killed the virus, or we used herd immunity, or we died. Now, that doesn't always work. Well, obviously, one of these first two did work for all of human history, or else we would have all been dead by now, right? So now our immune systems, it turns out, are really pretty good against most viruses, but some viruses have a very high fatality rate. Rabies is almost 100%. So our immune system can't help us there. And herd immunity doesn't work because we all die. If this rabies was as effective as influenza, let alone COVID-19, we wouldn't be here. Okay, but it's not. All right, you got to get bit by a dog or something, or another human that's got it. Smallpox is about 95%. And smallpox is probably the virus that has killed more people than any other. And the way we get herd immunity there is 95% of us die. And then Ebola is about 90%, but there we had a vaccine and we controlled it. So anyway, but most viruses have a low CFR, and that's good. And there's another way too. We've discovered vaccines. So that helps us to survive even the most virulent viruses. The first vaccine was introduced by a gentleman in England in 1796. That was a year before George Washington finished his second term. And that was for smallpox. And then the rabies vaccine was developed by Pasteur in 1885. So those were really the first two vaccines that were produced. And it's a good thing that we did the smallpox vaccine, because that turned out to be, it is a real killer. It used to be a real killer. So for example, between 1900, even after we had the vaccine, not everybody got it or could get it because of where they lived. The smallpox killed about 300 million people just in the first 70 years of 1900 of that century. 300 million people. Now, there really wasn't a pandemic. It just was continual. So it couldn't be called a pandemic. But I take it up to 1972 because that was when the World Health Organization declared that smallpox had been eradicated. And that's the only vaccine, virus, in fact, that we have eradicated. So now I'm going to show you the types of viral vaccines. This looks complicated, but it's not that bad. Okay, so first, you can get live attenuated vaccines. Now, what an attenuated vaccine means, it's just like in The Princess Bride. He's almost dead. Okay, this is a vaccine that's almost dead, but it's still alive. And so for example, if you took the polio vaccine, the sugar cube, you got the live vaccine. If you got a chickenpox vaccine or the very first shingles vaccine, or your children got the MMR vaccine, then they all got live vaccines, attenuated vaccines. Now that's really good because it's a long-lasting immune response, but the vaccines are alive, and if you got a health problem, you shouldn't get them because some people got polio from this vaccine, from the Sabin vaccine. And I can remember to this day, I got the sugar cube. I thought that was pretty good. It tasted really good. But anyway, now, of course, we don't get vaccinated from smallpox anymore because there's nothing to vaccinate against. Now, there's inactivated or killed vaccines, and these are dead, so they can't hurt you. And so the Salk vaccine, that's how the Salk vaccine was in fact a killed vaccine, but that was injection. Influenza, that's why we inject it. That's also as a killed vaccine. Now, they don't provide immunity quite as long, although it turns out that the Salk vaccine is really good for long lasting. But in most of them require booster shots or, doses every year. Sometimes it's because the virus mutates so rapidly, and that's the case in influenza. Now, there's this thing called recombinant vaccines, and that's the latest shingles vaccine called Shingrix. Or a hepatitis B vaccine also that you see advertised on TV. And what recombinant just simply means is that we modify bacteria so they make the vaccines. Now, if that sounds scary, it's not, because if you know anybody who is insulin-dependent diabetic, the insulin they take is made by a bacteria. Okay, so it's been around since the late 70s. That technique. So that was all happened before 1919. But there were the two groups that won the race, and you know what those are, Moderna and Pfizer. They won the race to create an FDA-approved vaccine. They used new types of vaccines. So now, almost every country is involved in this fight against COVID-19. That's good because we've got a lot to do, and we need to do it as carefully as possible and as quickly as possible. So the critical factors here, if you were a program manager, like I was in the Air Force for a while, actually quite a while, what the critical factors, it's always performance, schedule, and cost. Well, in this case, you have to have a very high performance, and you've got a very short schedule, namely as short as you can make it. But to a very good approximation, cost is irrelevant. So think of the Manhattan Project. We didn't worry about cost of the Manhattan Project. We wanted to build atomic weapons that worked, and we wanted to do them as quickly as possible. So we're trying to create vaccines that work, do them as quickly as possible, and we're not really worried about the cost. So anyway, that's where we are. Now, I still teach for Johns Hopkins as an adjunct, and my colleagues there tell me that about 15%, there's about 10,000 people total that work at Johns Hopkins, scientists and medical professionals. I'm talking about not staff folks. There's about 1,500 of them right now that work on COVID-19, and they collaborate with over 10,000 other scientists and medical professionals at about 1,000 universities, government, or NGOs. So if you add up all the universities, the government and non-governmental organizations and industry around the world, that adds up to about 1,000. So that's a lot of collaboration. Here's another thing that really helps us here. Every technical journal that has the slightest relevance to the coronavirus has started a rapid publication capability. So turnaround time sometimes is a day when it used to be months and months and months. Turnaround time is a day or two. And last year in 2020, over 60,000 papers, 60,000 technical papers on COVID-19 were published. That is unbelievable. So what does that mean? Okay, so first, never before in the history of our planet have so many, now first of all, not have so many engineers, scientists, and healthcare has worked on the same problem simultaneously. But it's possible now because we have the internet, right? So you can say, boy, the internet is bad, but in this case, it really helped us coordinate and virtually instantaneously publish our results. Second, because we're publishing so fast and it's not peer reviewed very well and all that, it's very sloppy, you're just putting it out there, putting it out there, putting it out. Some of the information today will prove to be only partially correct. And there'll be some information that we have that nobody else looks at except for the person that actually published it. But it's just overlooked. And it's later, 5 years and we'll say, oh, that was really important. Third, you can't keep up with it. Okay, you just can't. And fourth, please keep these things in mind. I'm going to tell you some things now that are not even close to what is currently in the public domain. Okay, but it's just some of it. What I do present will be necessarily oversimplified, and I want you to all be aware of a basic truism of science. Okay, this is something that some people can't understand. They say Fauci was wrong. He told us a lie. No, he didn't tell you the lie. He told you the truth to the best degree that science knew it at the time. But what makes science a science, what makes science science, is that it is falsifiable. Better evidence will come along, and then they say, oh, okay, yeah, okay, I got it. That was false. That was, okay. And so anyway, you always be aware of that. What makes science science is that it is falsifiable. Now, a lot of people have opinions that in their mind are not falsifiable. Can't do anything about that. But science is falsifiable. Okay, so here are the 6 vaccines that are either being used now as a vaccine against COVID-19 or soon will be. By some counts, there's over 2,000 candidates, but here are the 6 current leaders. And these are actually not in order, they're not in any order, okay? Except that I grouped them in terms of, see, these 3 all have asterisks after them. And then these 2 have pound signs, and then this one has a plus sign. So I grouped them in order of the type of vaccine they are. So you've probably heard of AstraZeneca. You probably heard of Moderna and Pfizer. You probably have never heard of the 2 that are made in China, okay? And you may have heard of Johnson & Johnson. But so let's take a look at what this is. So these guys, these 3, their DNA, they're all DNA vaccines. That should mean something to you now. They're DNA vaccines, okay? And we let bacteria make them for us. They're relatively new. It's just like Syngrents. Then the pound signs are brand new, unprecedented. We've never had an RNA vaccine ever, never, never, ever. Now, Moderna and Pfizer have both been trying to make them for 10 years. And so we got lucky. If the pandemic had started 10 years ago, Moderna and Pfizer would not be in the chase because they wouldn't know how to do it. They couldn't do it with RNA. Nobody could do it with RNA. And then this one in China is it uses a killed vaccine, sort of like rabies, very old technology. Now you'll never get to use, unless you move to China, you'll never use these two vaccines that are now made in China. This one is actually being used right now, the equivalent of an emergency use authorization, and over 1 million people have been vaccinated. Well, I looked at that number 2 weeks ago, so it's probably 5 million by now have been vaccinated in China with this. This is going to come out about the same time that J&J does, probably the first week in February. They'll clear phase 3 trials. But Zeneca, Moderna, and Pfizer are all going now. Okay, so how were these vaccines made so quickly? Sometimes people think that, science, you just have this miraculous thing and you go out on the beach and you just pick up the technology and you make a new vaccine. Well, it doesn't work that way at all. So first, biotechnology has advanced in dizzying rate in the last 20 years. It's amazing what we can do now. For example, you can sequence and synthesize. In other words, you can determine the order of the units in RNA and DNA, and then you can sequence that RNA or DNA very rapidly. And when I say very rapidly, I mean very rapidly, in a matter of minutes or hours, depending on how long they are. And it's been automated. You don't use test tubes like we used to and everything. You put it in a machine. You just I want this. And then whatever happens back in the machine, they just make it. And it's an amazing process. Now, those machines are expensive, so not everybody has them, but you couldn't put them in a high school, for example. But so the Chinese scientists were able to publish a sequence of SARS-CoV-2 on January 10th, which was like a few weeks after the virus was first isolated. Now, they actually did it sooner than that, but we hadn't started the rapid publication thing yet. So they probably, it took 2 weeks to publish it. It wouldn't have taken that long now. So they actually got it done in December of 2019. Okay. Now, what did that mean? Well, Pfizer and Moderna, for example, synthesized the entire viral genome 2 weeks later, which was about the same time as the first confirmed case of COVID-19 in the United States, which was announced in 20 January. Okay. Now, why Pfizer and Moderna? And the reason is because they had been conducting research on RNA biotechnology for over a decade now, for different reasons, but they'd been doing it for over a decade. So without that decade worth of work, they would be out of the game. Okay, but they were there, and they said, "Aha!" Now Pfizer had invested $2 billion on a new RNA technology, and it just didn't work out for them. Now, we will eventually get that new RNA technology worked out, but Pfizer just quit. After 9 years, it just said, okay, we're not going to do that anymore. But now looked up and said, holy cow, the leaders of Pfizer said, we can use all that knowledge now and not work on this RNA technology, but we can make an RNA vaccine. Moderna, on the other hand, was trying to make RNA vaccines for a decade. And they finally became successful about the middle of 2019. Now, like the Geico lizard says, serendipity, right? For both of these guys. So that's why they were first out of the gate. They were able to start phase 1 trials before anyone else. And if you don't know what a phase 1 trial is, I'm going to explain it in just a second. But all the other companies, the other 4 that we mentioned, they were able to produce a vaccine quickly too, although they were a few months behind Pfizer and Moderna, because they were experts in the technique that they were using. All right. So, but vaccines have to be tested before they're approved. So we go to them in 3 phases. First, and now this holds true for any drug, but for a vaccine, it's a little different than say for a cancer drug, okay? But for phase 1 trials for a vaccine, the first thing you ask the question, does it harm the patient? I mean, if we inject the vaccine and the patient dies, well, okay, that didn't work. Phase 1 also tries to find out the best dose. So you have a small group of people. Phase 1 is usually only 10, 15 to maybe 30, and you divide them into cohorts. So a few patients get a low dose, another group of patients get a medium dose, and the other group of patients get a higher dose. Now, it'd be nice if you had enough and you could give them 10 different doses of concentrations, but you want to find out if it's safe enough. And you don't even care if it works or not. You're not even looking at that. You're just seeing, can I keep giving higher and higher doses until I get bad side effects, okay? But then if it's found safe and all of the people can with just minor kinds of side effects can survive the higher dose, then they go to phase 2. Now that's hundreds of people, and that does more safety tests as well as to see if the vaccine works. And so you take 700 patients and you watch them closely. Does the vaccine produce antibodies against the virus? Of course, you also test, because now you got a lot more people, you also test to make sure that nobody dies or doesn't get really sick or whatever. And for those that are looking for a second dose, does the second dose confer better results or not? And if it does, then you say, okay, we're going to go 2 doses. If it doesn't, then you say, well, we'll just stay with 1 dose. If the vaccine is found to work, then you go into phase 3. And now phase 3 involves thousands of people. J&J right now has over 65,000 people in phase 3s on 3 continents, okay? And they're usually in different geographic locations. And you're trying to get a very diverse range of ages and other things. And you give half the patients a placebo and the other half of the vaccine in a double-blind manner. In other words, neither the doctor nor the patient knows whether or not they got the vaccine or a placebo. And it takes months to complete because some of the patients have to become infected. So you're watching these patients all the time and you're giving them tests almost as if they were an NFL football player, right? All the time, because you want to see if they were infected with the virus, but did they overcome it? Okay, and so then if they didn't overcome it and they ended up in the hospital, then you hope that it turns out that they were given the placebo. But normally a phase 3 study is watched closely for many years, 3, 4, 5 years, not at all unusual, but not now, not this time. So because we got the first results of the phase 3 from Moderna and Pfizer, and they both requested approval, emergency use approval, and they got it. So now I'm going to answer a few questions. Why do the RNA vaccines have to be stored at a low or very low temperature? You probably know this now, I hope, right? DNA is very stable. RNA is very unstable.
Right.
So, let me see. I'm missing the first thing here. Oh, there we go. Okay. So the RNA used for Pfizer and Moderna is a small part. It's only a small part of the COVID-19 genome that codes for the spike protein, and only a part of that. The problem is that mRNA is a fragile molecule and would be quickly shredded into pieces if it was injected directly into the arm. So one way to protect, and I put the M in front of there, and I didn't really mean to do that because that's more complicated than it needs to be. But one way to protect this RNA is to put it inside a lipid bilayer. Now, and if so you do that, now it's protected, it'll last a little longer. And the added feature is that now it can fuse to a muscle cell, right? And get inside the human cell, because the lipid bilayer is on another lipid bilayer and just gets sucked in. And now it's inside the cell. And now once it's inside the cell starts to manufacture lots of the spike protein. now the RNA itself, it goes away in about a couple of hours, but now you've got hundreds, if not thousands of molecules of the spike protein inside the muscle cell in your arm. Some of that spike protein ends up protruding from the membrane of the cell. And now these foreign fragments are recognized, well, the fragments are recognized as foreign, and then you get the standard immune response, right? You get antibody production, you get killer T cell production, and then later, 6 months to a year, you get the memory B cell production. So for example, you need the memory B cell production when you get a vaccine. If right now all of us were exposed to polio, our B cell production cells for polio would kick in and say, oh, I see polio and I'm going to produce antibodies for it. 30 years, 40 years, 60 years after I got the vaccine. Okay. So now we'll look at a few other questions here. Here are the four. I think I've got four. For viruses that require 2 doses for maximum efficacy, can the time between doses be varied? Will one vaccine prove to be better than the other vaccines? Why not simply inject the spike protein directly into muscle cells and induce the production of antibodies rather than inject RNA so the muscle cells have to produce the spike protein? And what about the variant? Okay, so let's take them one at a time. Can the time between doses be varied? Well, the best answer is, because of the way the phase 2 and 3 trials were conducted, we don't know. Okay, that's the best answer. We don't know. And it probably depends on the vaccine used. Maybe Moderna and Pfizer, it probably is, they'll be the same. In other words, you can't extend the time, or maybe you can, whatever. But AstraZeneca could be totally different. Okay. Okay. So, all right, I will answer that question from, I guess, is it from Eileen? On what role do viruses play in evolutionary biology? Okay. Yes, I will. I'll answer that question afterwards. So best guess, we probably have some wiggle room. In other words, we probably can, but not between the minimum time. The minimum time probably has to stay what the phase 1 and phase 2 trials were. Right now, it's either 21 or 28 days. Maximum time, though, can probably be increased by maybe several weeks, maybe even months. The UK is thinking about going 3 months. I don't know. I mean, it might be okay. So we have to answer that question. Should we use up all the available? So, I mean, here it is. This is the question we have to answer. Should we use up all the available vaccine now, right, on everybody that we have, and then speed up the production of vaccine for the second doses? Can we get enough vaccine for the second doses before we extend beyond the maximum time allowed, which we don't even know for sure? Okay, so that's a real problem that the next administration is going to have to answer.
Yeah.
I'll tell you this, the first administration is not even thinking about this right now. So how will we know for certain what the optimum, minimum, and maximum time between doses can safely be used? We need to conduct the phase 2 trials all over again, this time with many cohorts. And we don't have time to do that. All right, next question. Will one vaccine prove to be better than the other vaccines? Best answer is it doesn't matter now. Okay, because here's my approach to the question. I'll take the first vaccine I can get. If I have a choice, my first preference is J&J's. And that's because it only requires 1 dose. Johnson & Johnson's only requires 1 dose. It's also a DNA virus, so it's very stable at room temperature. I mean, it's like, yeah. In fact, I'm convinced that Johnson & Johnson vaccine, when it comes out, when the pandemic is all said and done and it's over, this vaccine right here is going to be used mostly more than any of the others, and will vaccinate more people because you can ship it to Africa and not have to worry about dry ice. See, I got these out of order, but we won't know for several months. We don't know. The answer to this question is almost certainly, but we won't know for at least several months. I hope all my stuff doesn't turn out to be like this. Okay, so why not simply inject the spike protein rather than the RNA for the spike protein, right? I mean, we inject the RNA that makes the spike protein. Why don't we just inject the spike protein? Well, Here, I did it right. First, it's far, far easier to mass produce the RNA than the protein. And you say, yeah, but cost is not a factor, so who cares? Well, second, you're going to have to be injected almost certainly with a larger volume of protein than you would be injected with a volume of RNA. And it already hurts like heck, right, to get injected. So instead of 1 milliliter, you might have to get 50 milliliters. That's quite a lot, okay? And the side effects would probably be greater. Third, there are more complex reasons, but I'm not going to go into them. So for now, trust the scientist on this, okay? But remember, until all the evidence is known, they could all be wrong. Science is falsifiable, okay? All right, another question. What about the variants? A lot of mutations. I mean, the first mutations of the SARS-CoV-2 virus were popping up within 3 or 4 weeks after it was first published. But the genome is so large. Remember, it's over 30,000 base pairs long. 30,000 bases long relative to other RNA viruses. It's big. So most mutations have no effect, but a few mutations appear to affect its infectivity rate, but not its lethality. So nevertheless, a more infectious virus requires that the percentage of people who are immune to the virus have to be increased to keep the spread very low. So the initial infectivity of the virus, when it first came out, and the very first thing that we looked at, it looked like we would need about a vaccination percentage of around 70%. The new variants might require 80% vaccination rate or even higher, and that's a problem because some people will refuse to be vaccinated, and how large that is will probably be more than 20%. So this could be the most dangerous effect with the highest infection rate. Okay, so now let's see, I got another question here in chat. Let's see who that is.
Nancy.
Yeah, would it be a good idea to consider wearing a mask but not in public during any winter season? Oh, I think so, Nancy. And in fact, I think that one of the long-term effects of this is that we probably wear masks more often than we ever did before. I mean, if you went over to like Korea or Japan 5 years ago, a lot of people were in masks. Now in China, they were in masks because they were trying to breathe because the pollution was so bad. But now, Moderna and Pfizer have different cold temperature requirements. Okay, I'll answer that, then I'll answer Eileen's. Okay, remember I said that Moderna had been trying to make RNA work as a vaccine for 10 years. And so they have some secret sauce. Both Moderna and Pfizer encapsulate the spike protein RNA in a lipid shell, and a fatty shell. Moderna has some secret sauce that protects the virus, the very fragile messenger RNA, far better than Pfizer does. So in order to keep the Pfizer messenger RNA viable, it has to be frozen in very cold temperatures. Moderna, on the other hand, they know how to make the lipid shell, the fatty shell around the messenger RNA, so that it can survive at just, minus 0 degrees, 32 degrees centigrade or Fahrenheit, or a little lower than that. And it can last longer outside, at room temperature than the Pfizer vaccine. Now, you might ask the ethical question, since this is so important, right? I mean, it's very hard to get dry ice vaccines that require dry ice to Africa and expect them to survive, right? I mean, expect them, to pay for all of that and everything. Why doesn't Moderna come out and publish how they make their lipid shells? Well, that's a question you'll have to ask Moderna. I'm not going to answer it, but it does stand to reason that maybe they could, for the betterment of humankind, they could discuss it. Okay, now let me ask or answer. Is that okay? The person who asked the Moderna and Pfizer vaccines, is that Nancy? Nancy, does that answer your question? I think it was Nancy.
Yes, Larry,
yeah.
that's real helpful.
Okay,
Thank you.
now
Yes.
Eileen asked, okay, great, Nancy. Now Eileen asked an interesting question. What purpose do viruses play in evolutionary biology? Why do they exist? Eileen, I think the best answer to that is none. Viruses came before cells, basically. I mean, we had cells. Viruses came up because they were just pieces of RNA and DNA. And so the bacteria have been fighting viruses for millennia. I mean, not millennia, billions. Yes, billions of years longer than animals have, okay? They have a really neat immune system, put that in quotation marks, immune system to fight viral infections. And we just discovered this relatively recently, and that's what led to this latest biotechnology revolution called CRISPR. And that's another whole discussion if we ever wanted to get into that. But in any event, so Larry's perspective on that, viruses have evolutionary pressure on animal cells as mosquitoes do on humans. Okay, especially one species of mosquito called Anopheles. We don't need that. We could kill off that mosquito, and as far as we can tell, there'd be no ecological effects anywhere in the biosphere, except that humans wouldn't die of malaria. Okay, so anyway, I think to answer your question, there isn't any. There's no good. What purpose do viruses play in evolutionary biology, other than the fact that to kill us off? They have no purpose in evolutionary biology. And I guess you could say maybe that's a good thing, but I don't think so. What if people only get one dose? Ooh, okay, Nancy. So what the Moderna and that's a good question. For Moderna and Pfizer, one dose will give you, instead of 90% or 94, I think for 2 doses, you get 94%. For 1 dose, you get about 50%. So that's the reason. I mean, that's why you need 2 doses there. If someone has had COVID, should they get vaccinated? Yes. A relative feels her antibodies enough. How does she know she has them? She's also been opponent of other children's vaccines. Okay, well, if she's an anti-vaxxer, you're not going to talk with her. But but here's the thing, Jeanette. You could have COVID and even survived it and not necessarily generated the antibodies that are as good as the messenger RNA antibody, because you could have created an antibody against another part of the viral particle that's not the spike protein. And that will eventually, I mean, it could save you from a big viral load of the virus, of the vaccine, of the virus, but you don't know. Okay, you just, and again, I mean, the answer is, I mean, the best answer is we don't know. But right now the CDC says, yeah, get the vaccination. Okay, get vaccinated. But if somebody, but I mean, it's good if the anti-vaxxers had COVID-19, then that's better than nothing. Okay, let's see, I've got 3 new messages here. So why does my arm hurt so bad today after getting the Moderna first dose yesterday? Oh, hi, Nancy. And I think Ruth did too. Yes, and that's a good thing. That is a good thing, Nancy, because what that's showing you is that thing spread out and it's already inducing an immune response. So that's okay. Now, you'll survive your arm. I mean, it'll go away in a couple of days, okay? So anyway, so that's a good thing, okay? It's not a bad thing. It just means that you're going to make antibodies. Do you feel with various environmental disturbances, we'll be experiencing more pandemics sooner rather than later? Oh, that's a great question, Sue. Okay, so so there are a lot of books written on that, but if you don't want to read a big thick book, there's a lot of them. Here's what I suggest you do. You go into a Google search engine and you type in Bill Gates, you type in TED Talks, you type in pandemic. And he has 3 great TED Talks. One he did in 2015, way before any of this was, to tell everybody we're not prepared for the next pandemic. The next one he did was in March of 2020, March of last year, just as the pandemic was getting started, say, okay, we screwed up, we're not prepared for it, but here's what we have to do now. And of course, we didn't do that. So then he had another TED Talk in July and said, okay, since we screwed up, this is the possible outcomes of screwing up so badly. You know, and he had the best possible outcome to the worst possible outcome. And so all 3 of those TED Talks are great. So anyway, and that would probably be the quickest way. What is the best strategy to get vaccinated? I don't know that, Warren. I'm on a list, but I don't. Yeah, I don't know where to get the vaccine either. I mean, I don't know. How long before, if ever, we achieve herd immunity? Yeah, hi, Adrian. I would say that we will achieve herd immunity, quote unquote, after the vaccine has been out about a year, and at least 75 to 80% of us have received the vaccine. We have herd immunity now for polio. Okay, so, you know, because enough of us have taken it. Now, some people have stopped getting the polio vaccine, and we have actually had polio. People get polio. Isn't that incredible? In the United States. I mean, it's just unbelievable. But to a first order approximation, we have herd immunity on polio and most, measles, mumps, chicken pox, everything else. So even though 15, 20% of the people don't get vaccinated anymore, we still have herd immunity. And so about a year from now, yeah, we'll have herd immunity then. Maybe sooner. My hope is sooner. My hope is that by this summer, we'll be able to get back to somewhat normal and be able to eat in restaurants and things like that we used to. What about international travel? Good question, Jan. I think that, Deb and I are signed up for the trip to Rome in next November. I'm pretty sure we can do that. Yeah, I think so. Yeah, I think we'll eventually get through international travel. Now, there may still be some countries that won't let us in, but I think that I think we'll be okay in 6 months, 9 months, something like that. Those are all really good questions.
So Larry, 40 days after you get the second dose of your vaccine, what will you do differently from what you're doing today?
Okay. Depends on when I get that vaccine, Russ. That's a very good question. But if I don't get it until July or August, I'd be doing a lot of different things because everybody else would get the vaccine before me. But if I got it like next week, I wouldn't make any changes. I'd still wear my mask everywhere I go. I'd still minimize, how often I go to King Soopers. I'd watch what hours I went into King Soopers. I try to go in when there weren't a lot of people, if I could get away with it. Yeah, I know that I got this thing from Jeanette. Several friends and I who are over 70 received through Kaiser, even as non-members. So we called the number on their website, and after 2 phone calls with an hour wait time each, we got appointments. That's great. Okay, so I do look forward to your critiques on whether or not I was too technical or whatever. I normally have all sorts of diagrams and molecules and everything, but I cut most of that down. So, at any event,
Thanks.
but those were really great questions. I had not expected what purpose do viruses play in evolutionary biology. I mean, that's such a great question. If you get the Smithsonian or National Geographic, and unfortunately I can't remember which one it was, but they had an excellent 5 or 6 page article on should we kill off, I mean, actually drive to extinction the species of mosquito that causes malaria? So, I mean, there's an ethical issue there. Should we intentionally cause a species to go extinct? Now we've done it unintentionally, right? The passenger pigeons is probably the most famous one. The dodo bird's another one. I mean, there's lots of species of animal that humans have driven to extinction. But should we do it with, malice and forethought? In my opinion, Larry's opinion, for malaria, the mosquito that causes malaria, yeah, let's get rid of that guy. So anyway.
Well,
Okay.
Larry, thank you very much. This has been fantastic. I'll turn off the recording. We'll, if there are any final questions, people can